Hey everyone, and welcome to today's Explainer. We're jumping right into something I find absolutely fascinating: how LangGraph workflows actually work under the hood. Now, if you've been messing around with AI lately, you know that getting a model to answer a single one-off question is pretty trivial at this point. But what happens when you need to build something way more robust? Today, we're going to completely unpack the mechanics of building complex, multi-step agentic workflows using LangGraph and Python. We'll be turning all that high-level theory into practical, structured knowledge. Because, let's be honest, here's the real problem. What actually happens when your AI needs to query a custom database, or remember context from a message the user sent 10 minutes ago, or, crucially, give you some visibility into why it made a specific decision? Standard single-turn AI setups handle basic prompts beautifully, but the second you throw real-world complexity at them, they get incredibly fragile. And developers usually end up building this massive, messy web of custom plumbing just to keep it running. But thankfully, there's a much better way. So, here's our roadmap for today. First, we'll look at moving beyond single-turn AI. Then, we'll dive into the core primitives: state, nodes, and edges. Third, we'll tackle managing conversation history. Fourth, we'll unpack tools and the reasoning loop. And finally, we'll wrap up with persisting long-term memory. All right, part one, beyond single-turn AI and moving past those simple prompts. If you've tried escaping the limitations of a single prompt cycle, you know it usually requires a ton of custom coding. You're suddenly forced to manually handle those single-turn limits, figure out a way to remember context from earlier messages, securely query external databases, and somehow provide visibility into what the model's actually deciding to do. LangGraph tackles this by giving you a clean, unified structure. Instead of writing bespoke code for literally every scenario, LangGraph treats your agent as a graph. That means every single reasoning step, every tool call, and every response becomes a visible, inspectable part of the execution flow. Moving right along to part two, state, nodes, and edges. These are the core primitives. These three primitives are essentially the holy trinity of LangGraph. If you get these right up front, it's going to save you massive confusion later on. So first up is state. In LangGraph, state is a typed dict that acts as the shared memory for your entire application. Think of state like a giant conveyor belt. It carries the complete message history through every single step of your workflow. Every node reads from this belt, and every node writes its updates back to it. Nothing passes between your nodes in any other way. And the cool part? If a node doesn't update a specific field, that field just stays unchanged as it rides the conveyor belt to the very next step. Next up, we have nodes. So if state is the conveyor belt, nodes are the actual workstations along the line, and they are literally just plain Python functions. A node takes the current state as its argument, does some actual computational work like, running a language model, and then returns a dictionary containing only the specific fields it wants to update back onto that conveyor belt. The beauty here really is in the simplicity. You don't need some crazy decorator or a convoluted base class to make a function a node. It's just standard, straightforward Python. And our third primitive: edges. Edges are your execution pathways. They act as the routing tracks that define the strict order of operations. An edge can just say, hey, after node A finishes, go ahead and run node B. Or it can use conditional logic to call a routing function and go wherever that function dictates based on the current state. Now, keep in mind, every single graph explicitly requires a starting entry point and at least one defined path to an end. Okay, part three, managing conversation history and how we accumulate state automatically. Now, for conversational agents, your state needs to carry the full history of user inputs, model responses, and tool outputs, so the model always has the right context. But by default, when a node returns a value for a state field, that new value completely overwrites and replaces whatever was there before. And for conversation history, erasing the past, yeah, that's an absolute disaster. This is exactly where a mechanical concept called a reducer function comes into play. By using a reducer, specifically one called add messages, new values append and accumulate into a list safely, rather than just wiping out all your previous data. And LangGraph actually provides a brilliant out-of-the-box solution for this. It's called messages state. It's a built-in state type that already has this appending logic fully wired in. It automatically handles the deduplication, the ordering, and the appending of message objects. This is huge because it entirely eliminates the need for you to manually write any of that messy array stitching logic. You just return a new message, and messages state ensures it gets perfectly tacked on to the end of the ongoing conversation. Let's move into part four, tools and the reasoning loop, often called the React pattern. We all know a language model is great with its general training data, but if it needs to interact with your specific proprietary data, like checking a user's subscription tier, it needs tools. So let's break down those invisible mechanics of the React pattern. It basically happens in 3 distinct steps. First, the model assesses the user's prompt, decides it needs external data, and populates a tool call instead of just replying with text. Second, a specific node called a tool node reads that request and physically executes the bound Python function. Third, the result of that function gets passed back to the model, which then synthesizes the final answer for the user. Let's trace exactly how this happens step by step, because this is a real aha moment for understanding how the model communicates. Step 1, the user sends a human message asking for a customer's plan. Step 2, notice the model doesn't answer directly. Instead, it outputs an AI message containing a tool call requesting to run the Get Customer Tier tool. Step 3, the system executes that tool and appends a tool message containing the result. In this case, let's say the word enterprise. Step 4, the model, now seeing this complete history on the conveyor belt, generates a final AI message that says, Customer Cust 1001 is on the enterprise plan. It's just a continuous loop of communication being routed through the graph's edges. But I do need to give you a critical reality check here, and it's highlighted perfectly by the source material. Every tool used costs 2 model calls, one to decide what to look up, one to interpret the result. I really want to emphasize this for anyone building real-world applications. This React loop is incredibly powerful, but because it requires 2 distinct trips to the language model per tool use, you have got to factor this into your thinking about latency and API costs. Because nobody wants a massive surprise cloud bill at the end of the month, right? Finally, part 5, persisting long-term memory and remembering across invocations. Up to this point, our graph processes a conversation beautifully in real time. But without persistence, every single time you call your graph, it's a completely blank slate. The AI forgets literally everything. To solve this amnesia, LangGraph uses what are called checkpointers. A really great example for when you're developing is the in-memory saver. A checkpointer works by attaching the graph state to a unique thread ID. Before execution, it restores that specific thread state, and after execution, it saves the newly updated state. Let's walk through a practical timeline to really illustrate this. Say on Monday, a user asks a question, and we assign this conversation a thread ID. Let's call it ticket 7741. The agent helps him out and looks up their account here. Now on Tuesday, that exact same user returns. Because we pass that same thread ID back into our checkpointer, it seamlessly restores Monday's state. When the graph executes on Tuesday, the agent already remembers the user's account tier from the day before. It doesn't need to ask again. It doesn't need to run the tool again. It allows for totally seamless, ongoing conversation separated by days or even weeks. So let's bring all of this together. The key takeaways here are foundational for understanding how LangGraph workflows actually work. First, absolutely everything communicates through shared state. Second, because of this architecture, your models, tools, and memory checkpointers are completely independent and swappable. You can swap out an entire language model or a database backend without redesigning the core graph. And third, which is honestly the most exciting part, these exact same primitives we just learned scale up effortlessly to massive multi-agent systems, where a coordinator routes requests to different specialist agents. You now have the blueprint. You know exactly how these agentic workflows function under the hood, all the way from basic state management to robust React loops and persistent memory. Which leads me to leave you with this final thought. Armed with these incredibly scalable primitives, what kind of multi-agent specialist system are you going to build next? The possibilities really are endless. Thank you so much for joining me for today's explainer, and happy building!